visual cell there. You see what I mean? This doesn't just respond to how the person looks, but to all kinds of other aspects around them. And some workers have referred to cells of this latter type as concept cells. Concept cells. They're no longer even purely visual. There must be a massive convergence of all kinds of different information from different sense systems onto individual cells. It really seems that that cell's activity in some way may represent that concept. Now, a big deal here is it really individual cells that do this? Could it really be that, if you went in your brain and knocked out the Jennifer Aniston cell, you'd have no idea who Jennifer Aniston was anymore? That's the idea that goes way back. And it is possible. It's more likely, however, the concepts are coded not in individual cells, but in groups of cells. So for a given concept, you probably don't have a single cell that's responsible, but you might have a surprisingly few number, maybe a few thousand of them, scattered around in temporal cortex or something like that. So very interesting, and if we had infinite time, we'd go on to this topic for a few more days, because there's all kinds of more interesting stuff. But it sort of is the culmination of a pyramid or hierarchical organization, or suggestion for how sensory systems work. You start off with cells that are sensitive to very simple physical features. You sort of combine those together to get cells that are sensitive to more complex things, combine those together to get still more complex things, and so on, up along hierarchy, until you have cells that may recognize the concept of a given person or a given object, regardless of the sensory realm in which it is presented. Okay, so I feel sorry to leave this because there's lots more cool stuff we can talk about, but we have other topics we have to get to. And we will return maybe a little bit later to say a little bit more about high-level sensory processing. So you draw a line right there. So that's for the exam this Friday. Everything for now on is going to be for the exam coming up in another 5 or 6 weeks. Having talked now about sensory input, it's kind of time to reverse things and talk about the other side, motor output. And it's a remarkable thing. And this is one of there are a lot of things, I always like to say this, that are trite and trivial, but at the same time incredibly deep. And this is one of them. That the only way we can affect the world is by moving muscles. You might think, I'm a really intellectual sort, I think about things. Well, that's great, but the only way you can have any effect on anything is by moving muscles, or very occasionally by the secretion glands, although the actual secretion glands is probably the actual secretion, they involve a muscular component. Here's a quote relating to this from Sir Charles Sherrington. Does that name people know? How many people know who Sherrington is? Tis, because I mentioned this last semester, and I said there's thank you. And there were a few smattered hands, I'm happy to say it. It's like if there's two names you should know in the history of neuroscience, it would be maybe Cahal, whom I mentioned before, and Sherrington would be right up there as well. Sir Charles Scott Sherrington, he was primarily a physiologist. He worked largely in muscle systems, but among the many important things he did was he noticed that there was sort of a lag between the activation of one neuron and the activation of the next cell. It wasn't continuous. There was like a little temporal lag in between. And he noticed various other interesting aspects about the way that one neuron affected another neuron. And he came up with the idea that the most likely thing to account for this would be if the first neuron released chemicals across a little gap, and those affected the second neuron. In other words, Sherrington was the guy who came up with the concept of the synapse and the concept of chemical transmission at synapses. The existence of synapses wasn't proven until the late 1950s with the electron microscope, but Sherrington figured the thing out just based on the results of physiological experiments. So one of the very most important persons in the history of neuroscience for a whole bunch of different reasons. We'll talk a day or two about reflex mechanisms in the spinal cord, and all the original work of this was done by Sherrington as well. But here's a quote from Sherrington. Even in man, the crown of life is an action, not a thought. We can still endorse the old adage that to move things is all that mankind can do, and that for such, the sole executant is muscle. whether in whispering a syllable or felling a forest. So some people have sort of the view that movement's not that important, muscle is, just not that important or interesting a part of neuroscience, but it ain't true. Everything you do by moving muscle. Otherwise, it just stays inside you and it doesn't get outside. Just like he says, like Sharon said, whether it's whispering a syllable or felling a forest, muscle is the only way that everything going on inside of our brains ultimately has that effect. So movements are, of course, produced by the contraction of muscle. That's all muscle does. It contracts, it doesn't contract. And there are more complex aspects to this as well than you might realize. And again, let me spend just a minute or two showing you that maybe movement control perhaps is a more interesting thing than you might think it is at first blush. Here's just a simple example. Here's the leg of a cat, and cats were widely used in early work on muscle contraction. They're not as commonly used now, but in the teens and 20s of the last century, cats were the most common animal. And this is a cat which is simply allowed to walk on a treadmill. And these are a number of muscles in the cat. We don't have to worry about what they are, but here's 1, 2, 3, 4, 5, 6, 7, 8 different muscles in the leg of the cat. And the cat is simply walking on a treadmill, okay, nothing fancy. These are electromyograms, EMGs. Have you heard of these before? They might have been mentioned last semester. These are simply measures of the electrical activity of muscle. As we shall see in a little bit, muscle has an electrical component to its actions. And here's the important thing. Making a step, it seems like a rather simple movement, but look how complex the contractions of these muscles are. This one contracts a little bit at the beginning of the step cycle, then shuts down a little tiny bit at the end. This one has a big peak at the very beginning. This one is sort of a biphasic thing. It fires like twice. This one fires actually a couple different times, and we have ones that fire here. This one has this bi-peak thing. This is what you need to get the animal to take a step. Imagine you were sitting there with, how many of these are there? 6? 3, 5, 6, oh, there are 8. Imagine you were sitting there with 8 levers in front of you, and to get the control of these individual muscles, to get the cat to take a step, you have to move these 8 levers in exactly the right order, exactly the right way. This is just as true for our movements. There's a figure I saw like when I was in grad school about 200 million years ago, around with the dinosaurs. And I've almost remembered this figure. I've tried lots of times to find it again with no success. I think it's in the Handbook of Physiology, but I haven't been able to find it. But it was something analogous to this, except they had a person writing. And they put not 8, but like 20 different electrodes in the hand muscles, the forearm muscles, the upper arm muscles, the shoulder. And they had the person take a pen and write a letter, say the letter A, just as a for instance. Okay? Well, what you see is something like this, but even more complicated. There's like 20 or 30 different muscles when you just draw the letter A. 20 or 30 different muscles are contracting for precise little moments, precise little bits of this movement. You see what I mean? If you had to think this out, if you had to think, well, the helicis brevis is going to contract for 24 milliseconds followed by, etc., you couldn't move anything. You'd be frozen trying to figure out what things to move. And yet you do this all the time. And it's really incredible. You don't even have to think about it, right? It just happens. You just think, write an A, and your brain somehow figures out 20 or 30 different muscles, each one contracting for exactly the right length of time to give you this nice, smooth letter A. And think about this. Suppose you write an A with a pen on a piece of paper. Suppose you take a piece of chalk then and you write the letter A like a foot high, let us say. Still easy to do. You don't have to think about it anymore to write a big A than you do a little one, do you? And yet, if you think about it, these are completely different muscles that are involved. When you do think about it, it's mind-boggling. With no thought on your part, you can switch from one set of muscles to another set of muscles, make a huge, gigantic A. Again, no thought, no pondering in your things. You don't think, well, I'm going to have to engage my pectoralis major to make this upward string. You don't do that. Your brain just automatically does it, and the letter gets drawn. And if you think about it, this really is a pretty amazing thing. At some level, your brain must be working in terms of the letter A. And somehow that must get converted in a way that you're not consciously aware of, even though the computations are very complicated. This must get converted into exactly which muscles need to contract exactly when. I mean, imagine if you stuck a piece of chalk like between your toes and used the chalk to like draw a letter on the ground, you could do that pretty well, can't you? You probably never in your life, I guess, have drawn the letter A with your toes, and yet it would pose no special difficulty, would it? It might look a little messy, and you're not too skilled at it probably, but you'd still be able to just zip off and do it fairly easily. So there's a lot of interesting stuff to movement. At some level, you just decide what you're going to do, and some other brain system with little conscious involvement works out just how this movement will occur. Of course, the next step up the line is what makes you decide to engage in a certain movement. Remember I briefly said last time that I always thought I could go to my grave happy if I knew what happened when I was thirsty, and I reached out, picked this up, took the lid off, and took a sip. Well, you can see that movement is part of this, right? Exactly how do my muscles contract? And they have to combine with visual stimuli, because to know where the Coke bottle is, how do my muscles contract to get my arm to the smooth, almost graceful way, reach out and pick this up. But of course there's another step. How did I decide at that exact moment that I wanted a sip of soda? That's sort of an even bigger problem. That's the problem of motivation, to which we'll be turning a little bit later. So we've talked a little about sensory systems. We're talking now about how movement occurs. In a way, the most interesting question of all, in a way, is what makes you decide to do things when you do. That's what we'll talk about later. I just wanted to give you a little teaser for it now. Movement is produced by muscle. In mammals, there are 3 types of muscle. The one we will be talking about overwhelmingly the most is a muscle that moves your limbs around and so forth. This is skeletal muscle, also known as striped muscle, or as striated muscle. What does striated mean literally?
Striped.
Striped. So these two are just the same in English or anglicized Latin. Skeletal, striped, or striated muscle. Second type is cardiac muscle, found basically only in the heart. And cardiac muscle is similar to skeletal muscle in how it works. We're not going to talk about it separately, but you should have heard of it. And number 3, the third major type, is smooth muscle. This is muscle which in general is not under voluntary control. It's a muscle that moves things through our guts and so forth. It's generally involuntary muscle under the control of the autonomic nervous system. The way in which, we're not going to talk at all about smooth muscle, except this is one further brief mention in a moment. The basic molecular mechanisms are similar, but the internal organization of smooth muscle is very different from skeletal and striated, although some of the same biochemical things are involved. We're going to limit our attention almost entirely to striated muscle. Okay, here we have a beautiful microscopic section of a few striated muscle fibers. These are longitudinal sections, so the fibers are running in this direction. Makes sense? So if this were like, say, your biceps, these fibers here would be running in this direction. Makes sense down the length of the muscle. Can you see why it's called striated or striped muscle? Muscle fibers are quite large, and it's striated. I could go on. In fact, one of the very first lectures I ever gave was on striated muscle. It was, again, about 100 million years ago. I was a TA in a histology course, which is no longer offered here, and the instructor was sick one day, so the night before, it's like, could you give the striated muscle lecture tomorrow? And I was absolutely terrified. My voice was quavering and stuff. I pulled it off. We'll see if I can do it. I'm not sure. I think you can see why it's called striated. Oh yeah, these are very large fibers, and strikingly, look at this one. The nuclei are at the very edge of it. This is characteristic of striated muscle. The nuclei are at the very edge of the muscle fibers, and look, here's one fiber with 1, 2, 3, 4 different nuclei. Striated muscle fibers are multinucleate. These are very unusual cells in this regard. They don't have a single nucleus, they have multiple nuclei. There are 2 possible ways this could evolve. There are 2 possible ways this could develop. What are they? What are the 2 ways you could get a multinucleate cell? There are actually a bunch of multinucleate cells in the body, and they occur in several different ways. Any thoughts? Well, you could have the nuclei divide, like you're going to have normal cell division, but the rest of the cell doesn't divide. Does that make sense? In that case, you'd have nuclear division, but it would all be stuck inside of one cell. That's one possibility. It's not the right one in this case. Well, what's the other possibility? You could have a bunch of mononucleate cells fused together. right? You could have a bunch of normal cells with single nuclei fused together. And that's actually what happens to give you these multinucleate striped muscle fibers. So they're caused by the fusion, they were produced by the fusion of embryonic mononucleate cells. Now you'll note we have alternating light and dark lines, correct? The dark lines are referred to as the A bands, and the light lines dividing them are referred to as the I bands. You'll see, you can call them a band, a zone, a line, anything along those lines. Let's get that. Just for contrast, here's a section through some smooth muscle. You can see this looks very, very different indeed, does it not? Here's a longitudinal section. Here's a cross section. It looks as different as could be. There are no striations at all in it. It would be another lecture to go over smooth muscle, but be aware of the structural differences. Smooth muscle can be striped quite strongly. Don't get the idea that skeletal muscle is stronger than smooth muscle necessarily. For example, the muscles in the uterus that expel the infant are among the strongest muscles in the entire body. All right, let's zoom in a little bit, shall we? And a lot of what we're going to be doing here is zooming in further and further. So here's just a slightly higher power view. You can see the dark A lines, correct? Labeled conveniently, A line. And if you look, it's not really too distinct. You might think it was an artifact. But if you look, can you see the inside of the A band is maybe a little bit lighter in color than the outer edges of it? Can you see that? We're going to see in the next picture in electron micrograph that that's not an artifact. That is real, that is true. So here's the A band with a faint lightening in the middle of it. You can see beautifully the light I bands. And you can see now that each I band has lying right in the middle of it a thin, darker line. That's the infamous Z band. The Z band. These letters all stand for things, but we don't have to know what they are. Historically, they were named in the 50s with electron microscopy, but most people don't even know what they are, so we don't have to worry. Okay so far? All right, let us see what the actual structure of muscle is that gives rise to these fibers. And there really is something beautiful about this. Muscle contracts, it's a series of little so-called molecular motors, but even at the light microscopic level, and beautifully at the electron microscopic level, you can actually see how it works. You can actually see what's going on. So let's look at a schematic first, and then we'll look at the real thing. So here's a schematic showing what we were just talking about. From here to here is one of the dark A bands. It's not shown, but if you were to draw a line there and there, that would mark off the darker A band. Sound good? To the sides of it, here's part of one I band, here's part of another I band. The A bands are dark in color, the I bands are light, and you can perhaps see why. There are two proteins which are primarily responsible for muscle contraction. These assemble themselves into filaments. They can either be very, very thin filaments, or they can be much thicker filaments. The thick filaments are referred to as myosin, and the thicker myosin filaments form the darker A band. That certainly makes sense, doesn't it? The thin filaments are a protein known as actin, and the I band is a region made up of the actin fibrils. Again, it makes sense, doesn't it? Thick filaments are going to be dark, thin filaments are going to be light. Now the actin filaments are held in place by a network of other proteins that runs at right angles to them. These other proteins form the Z bands. Does that sound good? So the actin filaments are attached to the proteins that form the Z lines or Z bands. Now if we go back just for a second to this previous figure then, there's one of the Z bands running along, and you can see the thin actin fibers extend out on either side of it, attached to the Z band in the middle. And of course the dark A lines are where the thick myosin fibers are. Okay so far? Now let's notice just a couple other little things we can point out here. The actin and myosin fibers, you can see they overlap each other to some extent. So if you look at the A band, which by definition runs from here to here, you can see in the outer part of the A band, they're both myosin and actin fibers. Sound good? So if you were to cut through here, you'd have actin and myosin fibers. But if you cut in the outer part of the I band, you're going to just have the actin fibers. If you cut in the inner part of the A band, you're just going to have the myosin fibers. So the outer part of the A band is characterized by myosin and actin. The inner part of the A band is characterized just by myosin. Does it make sense that this outer part of the A band would be a little bit darker staining then than the inner part of the A band? Because the outer part you got both the actin and myosin. The inner part you just have the myosin. Makes sense. This should be a little bit lighter than that. Does that sound good? And remember I told you on this previous picture, and we'll see it much, much better, but if you look at this previous picture, you can very faintly see that the inner part of the A band is a little lighter than the outer part is. And it's going to turn out that's what that's due to, but we'll see it much better in a moment. There's one more very important term I have to introduce, and that is the following. Here's one Z band with the actin fibers attached to it. Here's the next Z band. This unit from here to here, so the whole thing from one Z band to the next Z band, is referred to as a sarcomere. S-A-R-C-O-M-E-R-E, a sarcomere. Sarco means muscles. Sarcoma is a tumor muscle, for example. Sarcomere, as we shall see, is the basic sort of functional unit of how muscle fibers work. Okay, so far, any questions? Now, this is not difficult, but there is a substantial confusion potential here because this vast array of new terms is getting thrown at you. But it's something, if you go over it a few times, it'll start to make sense. Here's a beautiful longitudinal electron microscopic view of striated muscle. And when this stuff was first done in the 50s, people just couldn't believe it. It's like they were seeing the heart of nature itself and seeing how it worked. Let's see if we can figure this out. Here, of course, is the dark A band. Make sense? Here's the I band. There's the Z line, correct? So the actin fibers are attached to it. And you can actually see, the thin actin fibers there, right? Here are the thicker myosin fibrils. And let's think this through. So we said before, looking at the previous picture, that if you look in the I band, you should just see the actin filaments and nothing else, correct? So here's what a cross-section through here would look like. See, these little dots are the actin filaments. So if you made a cross-section here through the I band, you would just see the thin actin filaments. We saw that the A band could be divided into two regions, an outer part where there's both actin and myosin, and an inner part where there's just myosin, correct? So again, here's what a cross-section through the outer part of the A band would look like. You'd have a mixture of the thick myosin and the thin actin filaments intermingled with them. Sound good? Whereas if we go to this inner part of the A band, and you can see it's lighter in color here. This is a region where there are myosin filaments, but no actin filaments. The actin filaments stop here. So if you go into this inner region, you have just the myosin filaments and no actin filaments at all. So if you compare this figure to that previous one, and go back and forth between them 600 or 700 times, you'll gradually get this up. It's really not hard. It is just confusing. Yes, sir.
So is a sarcomere one A band and two I bands? Because it seems to split right between.
Yeah, that's correct.
Okay.
Yeah, there's part of one I band. I mean, this whole thing is one I band. So this is half of an I band. That's the other half of the I band.
Okay.
So one half goes to one sarcomere, the other half goes to the other sarcomere. All right. So the A band now is, we introduce one more term. This inner part of the A band, where there are only myosin fibers and no actin fibers, this is referred to as the H band, or the H zone. Sound good? So the region that has just myosin, no actin, is the H zone, or H band. So if we look at this previous figure, this would be the H zone from there to there. Make sense? Just myosin, no actin. Everyone concur with that? So there's the H band, the central part of the A zone, just myosin, no actin. Only one more letter, and thank God we're done with all these stupid letters. I told you there's a nexus of proteins that links the actin fibers together, whoops, here it is, that forms the Z band. You can see running right down the middle of the A band. There's also another very thin vertical band. It's not labeled here, that's the M band or M line. And that again consists of a network of proteins that links the myosin fibrils together. Now if you think about it, here's sort of a model for how a little bit of muscle works. Now, if the fingers on my two hands were different sizes, yes,
Sorry, I
I
thought you
hope
were
you're
saying
sorry.
that the middle part was gonna be the lightest. But
Yeah, it is.
seems that it's the darkest.
oh, this is a very thin line right in the middle. It's so slender you don't really see it in a light micrograph.
Okay.
Okay, you can see it's just about as thin as the Z line, and it's against a much darker background, so it doesn't show in light microscopy. You can only see it in the electron microscope.
Okay, that's the H zone, very thin white lines that H zone.
Yeah, the thin white line you can faintly make out on the other would be the H zone. And then the M band here is not a light microscopic structure. You need the M to see it. Let's suppose that the fingers on my right hand were much fatter than the fingers on my left hand were. I've been tempted to like exercise my right hand like crazy while doing nothing with my left hand, just so I could give a good demonstration. But can you imagine these fingers are thicker than these? And imagine them sort of interlaced like this. Do you see what I mean? That would in effect be kind of a model of how muscle fibers are. Here'd be the thick myosin fibers, here'd be the thin actin fibers, and they're kind of like sort of alternating, more or less, like that. So, and we will see this analogy will come in very useful in a couple of moments in a slightly different way. Okay, so there's our basic structure of muscle. And here's a figure I always love. This is actually from insect muscle. And what's striking is this basic mechanism of muscular contraction that I'm describing was worked out by our distant ancestors. We share the same basic muscle mechanism with invertebrates. So if you see an insect hopping around, their muscle is working basically, there's some minor differences, but it's basically the same way as ours is. And this is one of those really early success stories. Before vertebrates and invertebrates split from each other, we're talking in the ancient evolutionary past, this basic mechanism of muscular contraction was worked out. This is a cross-section through insect muscle. Here it is blown up. I always just thought this was a beautiful picture. Extreme regularity in nature always impresses me. But here's a cross-section through insect muscle. These thick things are, of course, myosin fibrils. Does that make sense? And you can guess what the thin things are then. Those, of course, are the actin filaments. But just look at the perfect geometric regularity of this. It's like you've drawn it out on graph paper, isn't it? Look at one of these myosins, beautifully surrounded by 6 actin filaments in a perfect hexagonal array. So an ancient secret mechanism we are unraveling here. Well, the next step is this. Muscle does, as I hinted at before, muscle does one and only one thing. When it works, it shortens. That's all muscle does. It gets shorter. Muscle can't actively push. All it can do is shorten and pull. So when I flex my forearm, what's happening is this muscle, my biceps, is shortening. As it shortens, it simply pulls on the bones in the lower part of the arm, causing it to bend up this way. If I stretch my arm, it's this muscle contracting. My biceps can either shorten or do nothing. That's all it can do. So it's very interesting. Again, this work originally dates back to the 50s and early 60s. It's possible to take muscle fibrils and do electron microscopy on them from an animal when they were removed, either in the contracted or the relaxed state. Does that make sense? Actually, the simplest way is to take a muscle fiber, put it in some medium that would cause it to contract, and then throw it in the fixative. So here we have sections through muscle fibers of a muscle that was either completely relaxed or was maximally contracted, maximally shortened. Sound good? So let us see how many differences between these two we can observe. And these differences are going to be the basis to understanding what happens. How about sarcomeres? How do the sarcomeres differ in the relaxed and contracted state?
Shorter.
Yeah, so number one, when the muscle contracts, the sarcomeres shorten. In other words, the Z bands move closer and closer to each other. Sound good? That's number one. How about the I band? Number two, how does the I band change when the muscle contracts? Compare the I band here, it goes from there to there. Compare that to the I band here, which one is thicker?
Shortens.
Yeah, so when the muscle contracts, the I band becomes much, much smaller. Now again, to understand this, you have to keep in mind what these various things are. The I band is the region where you just have the actin filaments and then nothing else. How about the H band? The H band, you'll recall, is a region where you have myosin and nothing else. Here's the H band on the top one. See, it goes from there to there. Does that make sense? Look in the bottom, you can barely see the H band. It's right up next to the M line. See it there? Here it is on the top one, it goes from there to there. On the bottom contracted one, it goes from there to there. It's so narrow, it almost disappears. Can you all see it on the bottom? So that's number three then. The H band becomes enormously smaller when the muscle contracts. How about the A band? The dark A band, does that change? No, that stays virtually identical, does it not? I mean, it's incredibly identical. These are from two different muscle fibers, but here it is in the top, there it is in the bottom. You can see they line up almost perfectly with each other. So when muscle contracts, the sarcomeres get closer together, the I bands and the H bands narrow, but the A band does not change. The A band does not change. So to understand what happens when muscle contracts, we have to have a theory that accounts for these four changes that I've just mentioned now. Does that sound good? Well, here's a beautiful illustration. This actually looks a little bit like my artwork, but I stole it off the net. That illustrates apparently what's going on. The big theory, and at one time this was revolutionary, now it's absolutely accepted. It's not a revolution anymore. But the big theory is that the actin and myosin filaments, in effect, slide across from one another. This is sometimes referred to as the sliding filament theory of muscle contraction. It's sort of gone beyond the stage where it's a hypothesis. It's clearly established now. But actin and myosin filaments slide across one another. So this sliding filament mechanism of contraction. Look again at my hands, like I was saying before, and pretend the right hand is myosin, left hand actin. So the region, to start off with, there's only a small zone of overlap. Imagine these two slide across each other, like so. You see what I mean? Do you see how that's going to draw my two hands closer and closer together? That's basically exactly what happens. And again, you can go back and forth and compare these to that previous figure. Here's a schematic of what's happening in this figure. Here's a bit of muscle in the relaxed state. Here are the thick myosin, the thin actin filaments, the Z bands. Like we said before, the region in the middle here, where there's just the myosin, is the H band. So look here, there's just a little bit of overlap between the actin region and the myosin region. So the H band is very wide. It makes up most of the A band. There's just a little bit of overlap. But here's a contracted muscle. Imagine these were like actual little bars and stuff, and you could take the Z line and like shove this in. Do you see what I mean? Well, that's going to give you something like this. If the Z bands come closer together, just grab both these and push them closer together. If the Z bands are closer together, then there's going to be much more overlap, is there not, between the actin and myosin filaments? As a result, the H band in the middle is going to become much, much smaller. The I band is going to become smaller because the I band is the region of the actin filaments where they don't overlap the myosin, where there's just actin. Here, it's quite wide, but when you shove these Z bands together, a lot of the actin filaments now end up overlapping with the myosin, so the I band here becomes much, much narrower. Make sense, number two? So we got number one, I forgot what order I did it in before, but it'll be the same points. We got number one, the H band narrows. Number two, the I band becomes much, much narrow. Number three, the Z bands come closer together. And number four was that the A bands, or A lines, do not change their thickness. Well, you can see why that is. The A bands, their width is determined just by the length of the myosin fibrils. The length of the myosin fibrils simply doesn't change at all. So the A band stays unchanged. When the muscle contracts, much more of the A band is made up of the, much less of the A band is made up of the H band, the stuff where you have just myosin, but the actual A zone itself is unchanged because its width is determined by the myosin fibrils length. Sound good? So that, ladies and gentlemen, is the infamous sliding filament mechanism of muscle contraction. Truly a intellectual masterpiece that this has worked out. Now, of course, we're not done. There's obviously a question here. What is it that causes the actin and myosin fibrils to pull across each other, correct? Obviously, there's a big question that has to get worked out. What causes the filaments to slide? And it's not like these guys slide passively. They can generate huge amounts of force, correct? They generate just, they generate enormous amounts of force. I mean, I can pick this up, I don't know, it's about 20 pounds or so. What's doing that? It's actin and myosin filaments sliding across each other, exerting enough force to be able to lift this up. So the next question, obviously, is what causes the filaments to slide? I guess we'll start this today, we'll finish it next time. To understand this, we have to look in a little bit more detail at what one of these thick myosin filaments actually looks like. It's made up of a whole bunch, and we don't have to worry too much about the details. It's made up of a whole bunch of myosin molecules, each of which has a long tail, and at the end, it has kind of a fat head that sticks out. They talk about myosin heads. And a whole bunch of these bind together, like you can see here, to form one of those thick myosin filaments. So the key thing to note here is, out of this thick myosin filaments, made up of all these tails of the myosin molecules lying together, we got a whole bunch of these myosin heads sticking out. Now these myosin heads are the key to the entire thing. Because under the right conditions, in the presence of calcium, these myosin heads like to attach themselves onto actin filaments. So under the right conditions, myosin heads will attach onto actin filaments. And that's going to be the basis of the whole mechanism that we will describe. Should I start this now and not get through it? Oh, no. Well, I'll start it then. I'll do it quickly if need be, then we'll go through it more carefully next time. Does that sound good? Whoops. If you look around the net, you can find about 5 billion different diagrams of this. Each one has their advantages and disadvantages. This, I think, is one of the better ones. So we're going to very schematically see how this process occurs, how it is that the actin filaments are pulled across the myosin filaments, and you can kind of break the thing down into 4 steps. Some people break it down into more than 4, but 4 steps sort of gives you the essence of the procedure. So you could start anywhere along here. Let's start at this point right here, okay, number 1. We'll see it's a cycle. So here we have the myosin, the thick myosin filament. Here's one of those myosin heads that we were talking about before, okay? And here's the thin actin filament up on top. Now, this is under conditions where calcium is present. As I told you, in the presence of calcium, the myosin heads are able to bind onto the actin. All right, and again, we'll run through this a few times to see how it works. So calcium is present, the myosin head here binds onto the actin molecule. You'll note that there's an ADP attached onto the myosin head. Well, whenever you think of ADP, what other molecule should you instantaneously think of? ATP. And as you know, all the time, ATP is converted into ADP